In this video, we will be starting with introduction to organic reaction mechanism. There are many stages in organic reaction mechanisms. For that purpose, and these stages, they have different, there are some concepts that are applicable in the various stages in organic reaction mechanisms. Some of these concepts you can't do without. And that is why it is obligatory for learners to have a good knowledge of some of these concepts before targeting or treating organic reaction mechanisms. Some of the basic concepts in this organic reaction mechanism will include heterolytic fission. What do you understand by heterolytic fission in organic chemistry? As you know, the word hetero is not the same. They are different from the word hetero. It means different. Then we can say heterolytic fission, or what is generally known as heterolysis, is an uneven breaking of a covalent bond. An uneven breaking of a covalent bond. You know, in a covalent bond, a simple covalent bond has two electrons. The two atoms involved in the covalency, when there is heterolysis, heterolytic fission, when there's breakage in that covalent bond, the two atoms cannot live with the same number of electrons. One of the atoms involved in the covalent bond will live with more electrons than the other one. In that case, we say the more electronegative atom takes both electrons in the covalent bond. The more electronegative atom takes both electrons in the covalent bond. Let me give an example. An example in, let me say, hydrogen, excuse me, in hydrogen chloride, the bond is represented like this. We have this bond. We have this bond. There is hydrogen and there is chlorine. When there is heterolysis, what happens? This is the result. Okay, you now see that in hydrogen chloride bond, the two electrons there shared during heterolysis, during the breakage. What happens? The hydrogen atom, the more electronegative atom, which is chlorine, takes both electrons in the bonding. So all the two electrons used in the covalent bond are taken by the chlorine, which is a more electronegative atom. We can represent this in an equation form like this. We can say hydrogen chlorine to give but in this case something comes in which I wanted to know. The curly arrow, there must be a curly arrow here. The curly arrow there is indicating what? The movement of the pair of electron. This pair of electron that was used for the for covalent bonding has moved to a more electronegative atom, which is chlorine. Therefore, the curly arrow shows the movement of a pair of this electron to chlorine. So chlorine now takes the two electron, and hydrogen is bare. Hydrogen now remains with no electron. But remember, you might see some curly arrows which are like this. Some curly arrows could be like this. In that case, it represents only one electron. This one is only an unpaired, equals its unpaired electron. If you see um, uh, a curly arrow like this one, it is unpaired electron. But if you see a full one like this, it shows a pair of electron. This one shows a pair of electron. Okay, you should know that heterolytic fission also occur in compounds. It also occur in compounds with carbon and a compound with this bond, carbon CX bond. That is CX bond, X bond, where X is the more electronegative element, where X is the more electronegative. Where X is the more electronegative atom. And this X, which is the more electronegative atom, does what? It tends to draw electron towards itself. It tends to draw electron towards itself. I want to give an example of bromomethane. Bromomethane. Let me say bromomethane, e.g. Bromomethane. And in bromomethane, you will see that this is how it is in bromomethane. You will have a carbon O written as In this case, what happens in the reaction? You will have, because bromine is more electronegative than carbon, what happens? There will be, the curly arrow will move like this. There will be that movement, and the resulting product will be a CH3. This is a carbocation, and plus bromine, a bromide ion. That's a bromide ion with that lone pair of electron that it took from the bond. It could be represented in that form. So once more, we are saying that in heterolysis or heterolytic fission, this is an uneven breaking of a covalent bond, where the more electronegative element will go with both the electrons in the covalent bond. I've given an example. You will see how we'll be applying it. Another example is here, chloromethane. Yeah, there is still chloromethane in it. In heterolysis, you see the curly arrow that are moving. Now, they result in what? In a carbocation. It results in a carbocation, and this is a pair of electrons. This is a pair of electrons here. So this is an example of carbon chloromethane resulting in what? A carbocation and a chloride ion. Okay, beside heterolytic fission, there is another type of fission that occurs in during organic reaction mechanism. We call it homolytic fission. Homolytic fission. What do you understand by the term homolytic fission? What do you understand by the term homolytic fission? Contrary to what we did the other time, which was heterolytic fission, this one is homolytic fission. We can say this is a bond breaking where both atoms in the covalent bond will leave with one electron each. It's just the opposite of what we just treated. Just the opposite of what we have just treated. The other one was uneven breaking of the covalent bond. This one is even breaking of the covalent bond. During this even breaking of the covalent bond, both atoms in the covalent bond will leave with one electron. It should be remembered that this process requires a lot of energy. Homolytic fission, it requires a lot of energy. And in most cases, the energy required for the splitting or for the breaking of this bond comes but from UV light. An example of this, we want to still use HCl as an example. And the product that results from this even breaking of the covalent bond are what we call the free radicals. Let me use HCl to illustrate what I am talking about. This is a covalent. This is a bond again. This is what we call homolytic. Homolytic fission, homolysis. It results in That is chlorine there. Let's go for hydrogen. That is hydrogen there. Here, when this bond breaks, what happens? Hydrogen, since I said it results in even, this is an even break, this is an even bond breaking. An even bond breaking where the both atoms in the covalent bond leave with one electron. This is how it goes. Hydrogen will take back its electron, one electron in this bond. Then chlorine takes one again. I could still represent it through an equation form, which is when there is a break, when the covalent bond here breaks, when the covalent bond here breaks, it breaks evenly. One electron, there are two electrons here. One electron goes to hydrogen, and the other one goes to chlorine. And it is indicated by what? By the curly arrow. As I told you, the curly arrow, the one which is double-headed, is the double-headed O is refers to a pair of electron. But if it is only half, it means only one electron. So in this case, you see this type of arrow means only one electron is going one way. If it is this one, it means only one electron. But if it was double arrow, if the arrow was double, it means if the arrow was double like this, it means the pair of electron is going to one place. Because it is only just it's not a double-headed arrow, it's only one electron. This one signifies only one electron movement of only one electron. This one also signifies only one movement of only one electron. But a double-headed arrow signifies the movement of a pair of a pair of electrons. So let's continue. You will have hydrogen here. And you also have this one here. And we call these ones here free radicals. This is a free radical. This is a free radical. They are very, very reactive. This is a free radical. We call them free radical because they are having an unpaired electron. They are having an unpaired electron. Free radical having an unpaired electron. Having an unpaired electron. So what are free radicals? Free radicals, as you know, if I say what do you understand by free radical? Free radicals are these are very reactive atoms. A free radical is a very reactive atom or molecule that has a single unpaired electron. I said a free radical is a very reactive atom or molecule that has a single unpaired electron. So a free radical is a very reactive atom or molecule that has a single unpaired electron. Why I said they are very reactive is because you know here they have only one electron. Chlorine needs another electron to complete its octet of electron. Hydrogen needs one electron to complete to have at least two electrons in its outermost shell, in the outer shell. For that reason, they are very, very reactive. It should be recalled that free radicals, the reaction, and in most free radical reaction, they undergo three stages in their reaction. For instance, free radicals will undergo reactions like in the initiation stage, they undergo three stages in their reaction. Initiation stage, to what? To propagation stage, and finally to what? To the termination stage. Where in this initiation stage, you will see that the initiation stage is there is in this initiation stage where there is the formation of the free radicals. And now the formation of free radical at the propagation stage where a free radical now react with a molecule. Then at the termination stage, a free radical is reacting with a free radical. Well, when we go to reaction mechanism in alkanes, you will see that more better. So now, this is an example of what we have just another example of a carbon chloromethane. This is an example of a chloromethane molecule. In this chloromethane molecule, as I said, there is even breaking of bonds. When there is even breaking of bond, what happens? There's a breakage here. Let me just show. During homolysis, what happens? There's a breakage there where 1, 2, 3, 4, 5, 6, 7, they come but to this carbon atom. Then this other 1, 2, 3, 4, 5, 6, 7, they go back to chlorine. And this is how it is represented in an equation form. This is a free radical, and this is also a free radical. So in homolysis or homolytic fission, homolytic fission is even breaking of bond or even bond breaking, resulting in the two atoms living with one electron. And the result or the product of this even bond breaking is what? They are free radicals. And we say free radicals, these are free radicals, they have an unpaired electron, a single unpaired electron, and they are very, very reactive. Like in the case of chlorine, we say that for the formation of a free radical in chlorine molecule, it is initiated by what? By energy. Energy is required for the reaction to occur. For that reason, a UV light is very, very essential in this process. Okay, it drives us now to another concept. It drives us now to another concept we call electrophile. Another concept we call electrophile. You will be hearing of electrophile. What do you understand by electrophile? What do you understand, or what is an electrophile? What is an electrophile? That is a common concept that is usually used in organic reaction mechanism. What is an electrophile? The word electro has to do with electrons. Electro has to do with electrons. Electron loving, negative centers loving. These are species that will love moving towards negative centers, or that will love moving towards electron-rich centers, or rich centers. We can summarizingly say electrophiles are electron deficient species. They are electron deficient species. Electron deficient species. They are electron deficient species. These are electron deficient species, and they are generally positively charged. Most of these electron deficient species are electron species which are generally, or which are positively charged. Which are positively charged. An example of them are a proton. This is an electron deficient species. Electron deficient, they lack electrons. They don't have full electrons. They don't have full electrons. They are very, very unstable because they don't have full electrons. And very, very reactive. They are very, very reactive. So for that reason, we have things like proton. This is a carbocation, which we just talked of. We have things like NO2 plus, neutronium ion, and many others. Electrophiles are electron deficient species, which are positively charged. We said they are electron or negative centers loving. They love negative centers. You can still say electron loving, electron or negative centers loving. They love moving towards negative centers or towards electrons. They are positively charged. They love moving towards negative centers or electrons. They love electrophiles. Since they love moving towards negative centers, we say electrophiles are electron pair acceptors. We can still say they are electron pair acceptors. Electron pair acceptors. They are electron pair acceptors. We say they attack. We can say they are attacked, or they are attracted to electron-rich centers. They are attracted towards electron-rich centers. Attracted towards electron-rich centers. Attracted towards electron-rich centers. attracted towards electron rich centers, or they attack. We can say they are attracted or they attack electron rich centers. E.g., we can say the double bond. The double bond attracted or they attack. We can say they attack, or we can say they are attracted towards electron rich centers, or they attack electron rich centers. They attack electron rich centers, or they are attracted towards electron rich centers. We are talking of the double bonds. We can also say electrophiles undergo addition reaction. They undergo addition reaction. They undergo addition reaction. When they accept a pair of, since we say electrons are electron pair electrophiles are electron pair acceptors, we now say they accept a pair of electrons, resulting in the formation of a new bond. They accept a pair of electrons, resulting in the formation of a new covalent bond. Accept a pair of electrons. Accept a pair of they accept a pair or a lone pair of electrons. Accept a pair of electrons, resulting in the formation of a new covalent bond. That is what happens. So, learners, you should know what are electrophiles. As we have said, these are one of the concepts that we'll be using in our organic reaction mechanism. We said they are electron deficient species, which are usually positively charged. I've given an example. They are electron or negative centers loving, electron pair acceptors. They are attracted towards electron rich centers, or we say they attack electron rich centers. They attack electron rich center like a double bond. In a double bond, like in an alkene, they undergo what? Addition reaction with alkenes. When they accept a pair of electrons, resulting in the formation of they accept a pair of electrons, resulting in the formation of a new covalent bond. That is what an electrophile is all about. So this is an example of an electrophile. These are just examples of electrophiles, such as this one, bromine ion, bromine ion, iodide, nitrogen ion, carbocation, and these are all examples of electrophiles. So we say they attack or they are attracted to electron-rich centers, for example, double bonds. It drives us to the next concept, which is nucleophile. As the word sounds, nucleo, it has to do with the nucleus. And the nucleus is what? The nucleus is positively charged. The nucleus of the atom is positively charged. It has to do with nucleo. Nucleus. Nucleophile has to do with what? Nucleus. So we can say uh, there are these are nucleus loving. We can say they are nucleus loving or positive centers loving. Generally, electrophiles are electron rich centers. Electron rich centers. They are electron rich centers. They are electron rich species. Sorry, they are electron rich centers. Yes, still yeah, but use the word. They are electron rich species. They are electron rich species, and being electron rich species, they carry a partial positive charge. They carry a partial negative charge or a negative charge. They usually carry a negative charge or a partial negative charge. They are electron rich species. They carry a negative charge, or a partial negative charge. Negative charge. Some of them, an example of them include halides. Like let me say, an example will include halides. Halides, yeah, that is the chloride, the bromide, the halides. Example will include the halides, halide ion, yeah, halide ions. They will also include the hydroxide ion. Some will even include the cyanide ion, and molecules. And molecules with lone pair of electrons, and molecules with lone pair of electrons. So, nucleophile, as I said, they are electron-rich species. They carry a negative charge or a partial negative charge. Examples are the halide ion, hydroxide ion, the cyanide ion, and molecules, many others, and molecules with lone pair of electron. An example of molecule with lone pair of electron, we have a water molecule, we have ammonia molecule, water molecule, ammonia molecule, there is ethanol, and others, and others. As we said, as electrophiles were doing theirs, they are electron pair acceptors. On the other hand, nucleophiles are electron pair donors. They are electron pair donors. They are electron pair donors. Because they have molecules with lone pair of electrons, we now say they are electron pair donors. They are electron pair donors. When an electrophile donates a pair of electrons, they result in the formation of a new covalent bond. And the electron division species that electrons are being donated to is under attack. If a lone pair of electron is donated to an electron division species, what happens? That electron division species is electron division atom is under attack. Let me give an example so that you can understand better. This is an example of it. I still want to use the reaction between, let me say this is H3 plus the nucleo. This is the nucleophile here. This is the nucleophile. I'll put a touch there. This is the nucleophile. What happens? What happens? Movement of the curly arrow indicates the movement of what? Indicates the movement of the lone pair of the lone pair of electron, and this result in what? This result in this molecule H3 the same thing that result in that molecule. I could still go to the formation of this other molecule here. Let me use this one. I have CH3. There is a carbocation, a tertiary carbocation. What is the resultant molecule? That is the resultant molecule. So this is how the whole mechanism moves. So as I said, when a nucleophile donates a pair of electrons, this results in the formation of a new covalent bond. With the electron division atom under attack, this is a carbocation, a tertiary carbocation. The atom, the electron division atom, this is the electron division atom here. The carbon, the positively charged carbon, the positively charged carbon is under attack, as the nucleophile is donating this pair of electron here. This one is under attack, resulting in what? Resulting in a new covalent bond. Okay, so I've given you, there are many examples of nucleophiles. Hydroxide ion, you can see them here. The cyanide ion, this is a lone pair of electron. There are lone pair of electron on the hydroxide ion. There are in water, you have a lone pair of electrons there that can be donated. Electron pair donors. Ammonia, on the nitrogen atom, you have a lone pair of electron there that can be donated. So generally, these are electron pair donors. They have electron pairs on them that they can use in donating to an electron deficient species. We call the electrophile. Thank you. It moves us to what we call the carbocation. This is another concept that will be used in the course of our organic reaction mechanism. A carbocation. What do you understand by a carbocation? What do you understand by a carbocation? The word carbo. Carbo has to do with carbon. Cation has to do with what? A positively charged atom. Carbo has to do with carbon. Then cation, the cation has to do with what? A positively charged atom. Or a positively charged ion. In other words, we can call it a carbonium ion. The words are used interchangeably. So, a carbocation or a carbonium ion is an alkyl group. This is an alkyl group with a single positive charge on one of the carbon atoms. I say it is an alkyl group with a single positive charge. This is an alkyl group with a single positive charge on one of its carbon atoms. So it is a carbocation is an alkyl group with a single positive charge on one of its carbon atoms. These carbocations are usually formed in organic mechanism. They are formed in organic mechanism, especially when they are linked to strong electronegative atom, as I showed you the other time. They are formed during organic reaction mechanism, especially when they are linked to a strong electronegative atom. For instance, as I said the other time, I talked of bromomethane. I talked of bromomethane as H3, the bond bromomethane to give a CH plus so now I'm showing the curly arrow showing the movement of the lone pair of electron when it is a double-headed. So when the covalent electrons that are here, they move to bromine, what happens? The CH3 becomes what? Electron deficient and acquires what? A positive acquires a positive charge. Meanwhile, bromine that takes all the 2 electrons that were used in covalent bond, does what? It acquires a negative charge. And this usually occurs in heterolytic fission. Heterolytic fission. So this is the carbocation. This is the carbocation that is being formed. Of course, there are 3 types of carbocations. There are 3 types of carbocation. We call them the primary, secondary, secondary, and what? And tertiary. Carbocations. We have primary, secondary, and tertiary carbocations. Let me just illustrate it here so that for you to better understand. Let me illustrate it for you to better understand. let's say for this molecule, this molecule will result in substituting all the hydrogen atoms attached to this ion, to this carbocation. We will have one. If one alkyl group substitute one hydrogen, we will have what? We will have a primary carbocation. This is how it is. This is a primary carbocation. A primary carbocation. See the movement of arrow. We call it primary carbocation. Now let's go to, if a second hydrogen atom is substituted by an alkyl group, we call it a secondary carbocation. This is how it goes. We denote it by a prime to show that it is a different group. This is an alkyl group, but it may not be the same alkyl group like this one. Then the arrow will indicate the movement of electrons. This arrow shows the movement of electrons, how electrons are moving towards the positively charged carbon atom. Thirdly, when the third carbon atom is substituted by an alkyl group, it results in what? It results in a tertiary carbocation. And this is how it goes. So this is secondary, and this is tertiary carbocation. A carbocation. Now, it should be noted that the arrow, this arrow here represent what? The arrow here represent an alkyl group. The arrow is equal to the alkyl group. The arrow is equal to the alkyl group, and the alkyl group could be a methyl group. It could be an ethyl group. It could be a propyl group. And so on and so on. A butyl group, the groups are becoming larger and larger depending on what they can do. So all these groups, we call them the alkyl group. The alkyl group. The arrow there represent the alkyl groups. And you know that these alkyl groups, as indicated by the arrow, has an effect on the on the positively charged carbon atom, it has an effect on the positively charged carbon atom. These alkyl groups, they have what we call electron donating power. They tend to donate electron to the positively charged carbon. So as they are donating electrons here, remember this carbon atom, the carbon atom or the positively charged carbon atom, there is a high density of positive charge in this region. There's a high density of the positive charge in this region here. The density of positive charge on the carbon is high. So the high density of the positive charge on this carbon atom has a role to play. With this high density of the positive charge on the carbon atom, the electron donating effect of this alkyl group will do something to do what? To neutralize it. So what happened is that the alkyl groups, these alkyl groups tend to do what? They tend to push electrons. They tend to push electron from themselves. They tend to push electron from themselves towards what? Towards the positively charged carbon, towards the high density of positive charge. And when they push electrons, the alkyl group is pushing electron from itself towards this positively charged carbon. This other one is also pushing electron towards the positively charged carbon, and this other one is pushing electron towards the positively charged carbon. What happens? They help to do what? They help to neutralize the positive charge here. By doing what? By reducing the charge density on the carbonium ion. And when they reduce the charge density on the carbonium ion, this makes the carbonium ion energetically stable. When the high density of the positive charge here is reduced by what? By the electron donating power of the alkyl groups, it makes the carbocation energetically stable. It makes the carbocation energetically stable. So we now say the alkyl groups have what we call a positive inductive effect. Positive inductive effect. The alkyl groups have what we call positive inductive effect. By doing what? By donating electron on the positively charged carbon. As they tend to push electron towards the positively charged carbon, they help to neutralize the high density of the positive charge there. For that reason, when many of the alkyl groups are donating electron into to the positively charged carbon, they help to reduce what? They help to reduce the charge density on the carbon atom, making it energetically stable. For that reason, the more the alkyl groups, the more the stability of the carbonium ion. And in this case, primary carbocation is less stable than a secondary carbocation, and a secondary carbocation is less stable than the tertiary carbocation. Summarizingly, we now say a tertiary carbocation with 3 alkyl groups donating electron to the positively charged carbon, having a high density of positive charge. That tertiary carbocation is the most stable among the 3. The tertiary carbocation is the most stable among the other carbocations. So that is why you can see them here illustrated in this form. This is the least stable, and this is the most stable. Alkyl group is the methyl group here, being substituted by the different carbon atoms. So that is why in a reaction like this one, this is, if let me say bromine is from here, and there is another bromine that is from here, and there is another bromine that is from here. This is a primary. It is formed from a primary carbocation. This one is formed from a secondary carbocation because there are 1 and the 2 alkyl group attached to it. And this one is formed from what? From tertiary carbocation, because there are how many? There's 1 carbocation, 2 and 3. And if these products are formed, let me say 2 bromo butane, and there is bromobutane, and there is 2-methyl propane. The major product will be 2-methyl propane, because it is formed from a tertiary carbocation. Thank you, learners. Thank you. So revise this so that you will be used to, so that you can apply them in our organic reaction mechanism. Thank you very much. Like, share, and subscribe so that you will continue watching all our videos.